Welcome to the second section on geodetics and coordinate systems, so let's make a start. By the end of this section, you will understand the universal transverse Mercator system. Second, you'll learn to use latitude, longitude, and depth datums properly. These are the foundations of defining position, whether at the surface or within the crust. Third, we'll cover the differences between the various norths, true north, grid north, and magnetic north, and how to correct magnetic readings so they align with true north. Fourth, you'll practice converting positions between absolute coordinates, like UTM, and relative coordinates, such as those tied to a local wellhead. Finally, you'll be able to explain vertical reference datums, which are essential in understanding elevations, depths, and water levels. As we progress, keep linking each concept to field scenarios. Think of well placement, collision avoidance, and regulatory reporting. Now we come to the Universal Transverse Mercator, or UTM system, the most widely used projection in our industry. UTM was developed from the Mercator projection by rotating the cylinder 90 degrees to make it transverse. Instead of lines of latitude and longitude curving, they appear as straight, perpendicular lines within each zone. This reduces distortion at higher latitudes and creates a practical grid system. UTM divides the globe into 60 longitudinal zones, each 6 degrees wide. Within each zone, distortions are kept small enough to allow accurate mapping for engineering and drilling. Unlike Lambert, which favours east-west areas, UTM works best for regions that run north-south. Because of its accuracy, ease of use, and global acceptance, UTM has become the standard in more than 60 countries, including most oil-producing regions. For operators, this means you can consistently map assets, plan wells, and share data internationally with minimal confusion. The key takeaway is that UTM provides a balance between global coverage and local precision, which is why it dominates in oil and gas geodesy. The UTM system is a rectangular grid, which means every position can be expressed as a pair of coordinates, northings and eastings, in meters. This makes it highly practical for engineering work, where straight-line measurements are essential. Each UTM zone has its own central meridian, with coordinates defined relative to it. Within the zone, north-south distances are expressed as northings measured from the equator, while east-west distances are expressed as eastings measured from an offset reference line. This setup ensures that all values are positive, simplifying calculations and reducing confusion. For oilfield work, this consistency is invaluable. Whether plotting well trajectories, locating pipelines, or defining lease boundaries, UTM provides a straightforward, universally accepted system. The key is that UTM translates the complexity of a curved Earth into a workable engineering grid. But always remember, it only maintains accuracy within its defined zone. Once you move across zone boundaries, distortions increase, and special care must be taken to manage the transition. This is why operators often keep all project assets within a single UTM zone whenever possible. Although UTM divides the Earth into standard 6-degree longitudinal zones, there are exceptions. Certain regions have been given non-standard sized zones to meet political or practical needs. For example, Norway requested that all its North Sea assets remain within a single UTM zone. As a result, zones 31V and 32V were adjusted, with widths of 3 and 9 degrees, respectively. Similarly, Russia requested extended zones such as 31X to 37X to simplify its mapping requirements. Zone X itself spans 12 degrees of latitude compared to the standard 8 degrees elsewhere. These exceptions highlight an important point. Geodesy is not only a technical discipline, but also influenced by political and operational realities. For oil and gas professionals, the implication is clear. You must always confirm whether your project area lies within a standard or non-standard UTM zone. Assuming uniformity could result in positional errors when working across international boundaries. This is another reminder that geodetic accuracy requires not just technical knowledge, but also awareness of geopolitical contexts. Let's break down the definitions of UTM coordinates. Northings represent distances north or south of the equator. In the northern hemisphere, 0 starts at the equator and increases northward. In the southern hemisphere, the equator is arbitrarily assigned a value of 10 million meters, and northings decrease as you move south, ensuring no negative values appear. Eastings represent distances east or west of a central meridian. To avoid negative numbers, the central meridian is given an offset of 500,000 meters. As a result, eastings range between roughly 166,000 and 834,000 meters within each zone. These conventions may seem arbitrary, but they simplify data handling and eliminate confusion. By keeping all coordinates positive, UTM avoids mistakes in data exchange between teams. For oil and gas professionals, the critical point is understanding what these numbers represent. A northing is always a distance from the equator, while an easting is always relative to a zone's central meridian. This clarity allows engineers, geoscientists, and regulators to work from a common, consistent framework. Here is a practical example of UTM coordinates. Suppose we have a rig located at Zone 31 North with coordinates 6,850,500 meters north and 410,250 meters east. What does this mean in practice? First, the northing tells us that the rig is approximately 6,850 kilometers north of the equator. The easting indicates its position relative to the central meridian of Zone 31. Since the central meridian is set at 500,000 meters, we subtract the coordinate 500,000 minus 410,250 equals 89,750 meters. This tells us the rig is 89.75 kilometers west of the central meridian. By combining these values, we pinpoint the rig's location unambiguously within the zone. Notice how the system avoids negative values, making it simple to communicate and plot coordinates. In drilling, this precision matters. A misplaced coordinate could shift a well by kilometers, leading to missed targets, potential collisions, or even legal disputes over lease boundaries. UTM makes positional data straightforward, but it requires careful interpretation. Always remember, northings give latitude position, eastings give longitude position, and together they anchor your operations to a global system. In the southern hemisphere, UTM works slightly differently. Let's consider an example. A rig at Zone 31 South with coordinates of 8,500,000 meters north and 610,500 meters east. At first glance, the northing seems to place the rig north of the equator, but recall the adjustment rule. In the southern hemisphere, the equator is assigned a false northing of 10 million meters. To find the actual distance, we subtract 10 million minus 8,500,000 gives 1,500,000 meters. This means the rig is 1,500 kilometers south of the equator. For the easting, we compare it to the central meridian offset of 500,000. In this case, 610,500 minus 500,000 equals 110,500 meters east of the central meridian. These conventions prevent negative values and keep coordinates straightforward across hemispheres. For oil field work, this uniformity simplifies operations in both northern and southern latitudes. However, you must always be conscious of which hemisphere you are in when interpreting UTM coordinates. Misunderstanding the false northing adjustment could displace your operations by thousands of kilometers, which is obviously unacceptable for precision drilling. Another concept we must address is convergence, the angular difference between grid north and true north. At the central meridian of a UTM zone and along the equator, grid north aligns perfectly with true north. But as you move east or west of the central meridian or away from the equator, the difference grows. This matters because geological targets are often defined relative to grid north, while directional surveys may reference true north or magnetic north. Without correcting for convergence, your well path could drift away from the intended trajectory. The practical takeaway is this: convergence is a predictable, calculable correction. You can always determine the angle between true north and grid north at your location and apply it consistently. It's one more reminder that positioning is not just about numbers. It's about ensuring that all teams, from geoscience to drilling, are working from the same reference system. Ignoring convergence may not cause massive errors over short distances, but across kilometers, the discrepancies accumulate into costly mistakes. The graphic illustrates the position of the magnetic North Pole as of 2020. Unlike true north, which is fixed at the Earth's rotational axis, magnetic north shifts constantly due to changes in Earth's molten outer core. Currently, the magnetic north is drifting at a rate of around 55 kilometers per year across the Arctic. This movement has real operational consequences. Magnetic north is what our compasses and many downhole measurement tools reference, so if you assume it is fixed, you introduce errors. For oil and gas, especially in high latitudes, these errors can be significant. The lesson is simple: never assume magnetic north is constant. Always consult the most up-to-date geomagnetic models, which provide declination corrections for your area. Modern survey software and service providers incorporate these models automatically, but as an engineer or geoscientist, you must understand the principle. Knowing that magnetic north is variable ensures you take the necessary steps to align your data with the fixed reference of true north. Magnetic declination is the angular difference between magnetic north and true north. This value varies by location and changes over time as the magnetic field shifts. In some places, magnetic north lies east of true north, in others west. Declination is expressed in degrees east or west, and it must be accounted for when interpreting survey data. This is important to understand because MWD survey tools measure the azimuth using magnetics. For example, a tool might record an azimuth relative to magnetic north, but the geological target could be referenced to true or grid north. Without correcting for declination, your well path could be misaligned with the intended target. Importantly, declination values are not static. They are updated regularly through geomagnetic models. This means you must ensure that the declination applied to your surveys matches the current date and location of operations. Ignoring or misapplying declination is a common source of directional drilling error. Think of it as translation. The tool speaks in magnetic north, but the plan is written in true or grid north. Declination is what keeps the two aligned. Okay, question. If each one of the declination lines on the picture represents 2 degrees of declination and red is positive, approximately what declination is Basra? I will pause a moment for you to look. Right, so Basra is at the bottom of Iraq, at the tip of the Persian Gulf. There is a red declination line that passes through it, which is positive 4 degrees. Geological targets are normally defined in terms of grid north, although in some regions, like Canada and Alaska, true north may be used due to convergence issues. Surveying tools like MWD systems typically measure azimuth relative to magnetic north. If you report this data directly without correction, it will not align with the geological model. Gyro tools, on the other hand, reference true north and do not require declination correction. The practical workflow is this. If your tool references magnetic north, you must correct it to true north by applying the declination, and then, if necessary, adjust further to grid north by applying convergence. Only then can you plot your well path consistently against the geological target. This chain of corrections ensures all datasets speak the same language. Remember, survey companies apply these corrections as standard practice, but as the operator, you must understand the principles to verify accuracy and ensure targets are being hit. Total correction combines both magnetic declination and grid convergence. The process follows a logical sequence. First, the MWD survey records azimuth relative to magnetic north. Second, we correct that to true north by applying the magnetic declination. Third, we correct from true north to grid north by applying the convergence. To simplify, we use the so-called ethical rule. Corrections toward true north are positive and added, while corrections away from true north are negative and subtracted. This ensures consistency in application. For example, if magnetic declination at your site is westward, it will be applied as a negative value. while eastward declination is positive. Convergence is treated similarly depending on whether it moves you toward or away from true north. This structured process removes ambiguity. By understanding and applying total correction, we guarantee that survey azimuths align exactly with the coordinate reference system used for the geological targets. In other words, it makes sure the data collected downhole matches the map you are drilling against. Let's walk through a worked example. Suppose an MWD tool records an azimuth of 225 degrees. The local magnetic declination is 8.437 degrees west, which we treat as negative 8.437, and the grid convergence is 4.268 degrees east, or plus 4.268. According to the ethical rule, we first add the magnetic declination, then subtract the convergence. So the calculation is 225 plus negative 8.437 minus 4.268. The result is a corrected azimuth of 212.295 degrees relative to grid north. This is the value you would plot against your geological model. Notice that the workflow is systematic and repeatable. It removes guesswork and ensures that all directional survey data can be reconciled with target coordinates. Service companies usually automate this correction, but it's important for drilling engineers and well planners to understand what is happening behind the scenes. If you know how total correction is applied, you can audit survey reports, identify errors, and maintain confidence that your wells are being steered accurately toward their objectives. Here is a visual of the correction process. Imagine three different norths: magnetic north, true north, and grid north. The measured azimuth begins with magnetic north, then shifts to true north once declination is applied. Finally, after subtracting convergence, we arrive at grid north, which is the reference for most geological targets. Visually, it's like rotating the compass needle step by step until it matches the grid overlay on your map. The key is consistency. Every dataset must be corrected to the same reference frame, or mismatches will occur. The diagram shows how each correction builds on the last, reinforcing the need for a structured workflow. In practice, survey data is always adjusted this way, but the visual reminds us that the numbers we receive are not raw. They are processed through a series of transformations. Understanding these steps helps prevent confusion when comparing magnetic survey readings, true azimuths, and grid-based geological targets. Coordinates can be expressed in absolute or relative terms. Absolute coordinates tie positions to a global system, such as UTM. For example, we might say a well is at 6,354,300 meters north and 262,744 meters east in zone X. This provides an unambiguous position on Earth. Relative coordinates, by contrast, express positions with reference to a local point, such as a wellhead. For example, we might describe a target as 1,200 meters south and 200 meters east of the surface location. Both systems are useful. Relative coordinates are convenient for operational execution, while absolute coordinates are essential for integration across teams, reservoir management, and collision avoidance. The important point is that relative systems must always be tied back to absolute systems. If they're not, data becomes isolated and cannot be shared or checked. In practice, drilling databases maintain this link, ensuring that local measurements connect seamlessly to global reference systems. This allows companies to coordinate operations safely and efficiently. Now that we've completed the module, let's revisit our objectives. First, we examined the most common map projection models and saw how each introduces controlled distortion. You should now be able to identify which projection is in use and what errors it introduces. Second, we explored the correct use of latitude, longitude, and depth datums to define precise positions both on the surface and within the subsurface. Third, we reviewed the differences between magnetic north, true north, and grid north, and learned how to apply corrections so survey readings align with geological models. Fourth, we practiced converting positions between absolute coordinates, like UTM, and relative coordinates tied to wellheads. Finally, we examined vertical reference datums and their importance in ensuring consistency across datasets. Together, these skills form a toolkit that allows you to interpret, communicate, and apply geodetic principles effectively in oilfield operations. That concludes our session on geodetics and coordinate systems. I hope you now have a clearer understanding of how geographic principles translate directly into oilfield operations. From map projections to datums, from magnetic declination to UTM grids, we've seen that positioning is fundamental to everything we do. Errors in geodesy can cost billions, while accuracy enables safe, efficient, and profitable operations. Please progress to the quiz thank you.